This is worksheet 4 of the atomic structure packet, and this is the worksheet where we are going to finally talk about the important exception to the rule that I have continually referred to since the beginning of this course. So, up until this point, we have talked about individual atoms of elements. So we've talked about sodium and how many protons and neutrons and electrons it has and how to describe where the electrons are found. And we've talked also about an individual atom, maybe of chlorine, how many protons and neutrons and electrons it has and all that good stuff. And so because we've been talking about just individual atoms one at a time, we've been able to assume that if we know the atomic number of an atom and we know its number of protons, that the number of electrons is going to be exactly equal, because atoms are always what we call neutral, meaning you have just as many of the positive charges, the protons, as you do the negative charges, the electrons. And that means if you add up the total charge, the positives and the negatives, they cancel each other out, and the total charge is 0, which is what neutral means. But there's an important exception to the rule, and that exception to the rule occurs when atoms start interacting with each other. So if you have a sodium atom and a chlorine atom and they're close to each other, they're going to interact, and that interaction is a chemical reaction. And the part of the atoms that really interact are the electrons. Because if you think about it, the protons and the neutrons are deep inside the nucleus. They're not really close to the outside. And in fact, the specific electrons that really do the interacting in a chemical reaction are what we call the valence electrons. So those are the electrons that are in the outermost shell. Now, if you think back to a Bohr diagram, that some atoms have just one shell, so its only shell would be its outermost shell, and some atoms have 3 or 4 shells, so the outermost shell is whichever one is the farthest out. Okay, and it makes sense that those would be the electrons that would interact because they're on the outside, so they're the most sort of exposed to the environment and the other atoms around them. All right, and so when atoms interact with each other, they either give away electrons or they steal electrons. And in doing so, they're no longer atoms, which are neutral and have equal numbers of protons and electrons, but now they're ions. Okay, and ions are atoms that have either gained or lost electrons. Now, you might be wondering why an atom would give away or steal an electron. So it's really going to be important to remember, as we start talking about ions, the number one goal of any atom. The number one goal of any atom is to have its outermost shell full. What does that mean? Well, it means that if all you have is a teeny tiny first shell, remember that K shell can only hold 2 electrons, okay, then that would fill your outermost shell. But for any other atom that has a second or a third or a fourth shell, so on and so forth, it takes 8 electrons to fill that shell. Why? Because s orbitals can hold 2 electrons total, and p orbitals, by the time you add up px and py and pz, can hold a total of 6 electrons. And so 6 plus 2 is 8, and now you have your shell filled. Okay, now you might be thinking, well, what if it's in the fourth shell and they have a d orbital? Well, it turns out, and this is sort of beyond the level of this course, so you might just need to accept when I tell you that d orbitals don't have to be filled. Okay, so as long as your s and your p orbitals are full and you have 8 electrons in your outermost shell, we consider things to be full. Okay, now I want you to think about the noble gases, group 18 or group 8A, right? The one way over on the right side of the periodic table. Noble gases are what I will refer to as really happy atoms, and that's because they have achieved the goal of putting 8 electrons in their outermost shell. If you look at the electron configuration of any noble gas, its outermost, its highest level s and p orbital are completely filled. Okay, and so noble gases are kind of like the snobby rich kids on the playground. They're not going to interact with other atoms. They're not going to give away their electrons, and they're also not going to steal their steal electrons from other atoms because they're already exactly where they want to be in terms of the number of electrons that they have. Okay? All right. So we have some vocabulary here. We talked about valence electrons, or electrons in the outermost shell. We talked about how an atom that has gained or lost electrons is called an ion. And it turns out we can be more specific than just saying it's an ion. There are 2 types of ions. Okay? If an atom loses or gives away its electrons, right, it's getting rid of negatives. So that actually makes it positive. Okay, I know that's like adding negatives, so it gets a little confusing. But if you're getting rid of negatives, you're going to be more positive. Kind of like as humans, if we get rid of our negative thoughts, it makes us feel more positive, right? Okay, so that type of an ion that's positive is called a cation. I remember that because when you spell the word cation, there's a plus sign, a positive sign in the middle of it, right? Okay, that T looks like a plus sign. And if an atom steals electrons, right, so it's gaining these negatively charged electrons, then it's going to be a negative ion, which we call an anion. Okay, so I remember that because anion spells out A, N for negative, ion. A negative ion. Okay, so if you have a better trick for remembering that, fine. That's how I remember it. All right, so I want you to take a close look at a diagram that I have here so we can really understand this idea about giving away or stealing electrons. Okay, this is showing a chemical reaction, interaction between the electrons of sodium and chlorine. Now, it's going to help if you have a periodic table out in front of you because these diagrams do a really nice job of showing where the electrons are located in the different shells around sodium and chlorine, but they don't tell us the number of protons or neutrons in their nucleus. So I wish they did, but we're going to have to fill them in. All right, so if we take a look at sodium, it's element 11 on the periodic table. So that means that we know it has 11 protons. And because it's an atom, right, they're not saying it's an ion yet, we can assume that that means it's got 11 electrons. Or you can also count the number of red dots since they have them drawn in. Okay, I want you to write this down with me. Now, when we look at chlorine, we can see on the periodic table that it's element 17. It's its atomic number. So it's got 17 protons. And we can count up the red dots, or we can assume since it's a neutral atom that it's also going to have 17 electrons. Okay, now here's what happens when sodium and chlorine get together. They realize that they can both benefit by interacting with each other. Okay, I want you to look at their valence electrons. Do you see how sodium has just 1 electron in its outermost shell? It's not a full shell. It's not happy. Okay, and the thing is that sodium could theoretically try to gain 7 more electrons to put in this outermost shell. So like 1, 2, 3, 4, 5, 6, 7. But trying to move 7 electrons around is just energetically really costly, and it's just not very realistic. Okay, so that's not actually going to happen. So sodium's next best option is to say, well, hey, if I got rid of this one little pesky electron hanging out in my outermost shell, that whole shell would sort of go away since there aren't any electrons in it, and my next innermost shell, this one here, would become my outermost shell, and if we count it up, we see it's got 8 electrons there. So sodium's looking to give away an electron. Right, not really out of the goodness of its heart, but because it would really benefit. It would make sodium more stable, lower energy. Okay, now chlorine is in slightly different situation. If you look at chlorine's outermost shell, it's got 1, 2, 3, 4, 5, 6, 7 electrons. It's just one away from having a full outer shell. So energetically, just trying to steal and gain 1 electron, that's doable. And it turns out sodium wants to give away an electron, chlorine wants to gain 1. They're a perfect match for each other. And so that's what's going to happen. And when that happens, that's what's going to create a chemical reaction, right? So what we're going to observe is maybe a color change or a change in heat. The chemicals are going to get cold or they're going to get hot, or maybe we'll see some bubbling, right? Maybe we'll see something like solid form in solution. Those are the things that we see that are evidence of electrons moving around. Okay, so the result, so that's what this is showing over here, right, is that sodium now only has just 2 shells, and both shells are full, which makes sodium really happy. Okay, now sodium, because it's sodium, is always going to have 11 protons, but let's count how many electrons it has now. Remember, it gave 1 away, so now it only has 10 electrons. Okay, now remember, protons are positive and electrons are negative. So if you've got 11 positives and 10 negatives, that means you've got 1 more positive than you have negative, right? So sodium now has a +1 charge, which means it's not an atom anymore that would be neutral. It's a cation. Okay, and chlorine, okay, because it's chlorine, it's always going to have 17 protons. That can't change, or it won't be chlorine anymore. But if we count it up now, yeah, its outermost shell is all full. It's got 8 electrons in it. But if we count up all those red dots, all those electrons total, it's got a total of 18 electrons. So it's got 17 positives, 18 negatives, which means it's got 1 more negative. So it's got a -1 charge overall when you add them up, which makes it an anion. Okay? So, since electrons have a negative charge, when chlorine gains an electron, it becomes negative. And when sodium gives away an electron, it becomes positive. Okay, so you got a little table down here that you can refer back to when you're working on some of the problems that go with this worksheet. Okay. So, the general rule for what we just saw is that if atoms have less than 4 electrons in their outermost shell, they're going to just try to get rid of those electrons, which means they get rid of negatives, they'll become positive cations. Okay, so that's true for all of groups 1A, 2A, and 3A. Okay, on the periodic table. And atoms that have 4 or more electrons, they're going to try to fill their outermost shell. So they're going to steal electrons from other places, steal negatives, become more negative, become anions. So groups 4A through 7A form anions. Okay, now noble gases, they don't, remember, form cations or anions because they already have 8 electrons. So that last column on the periodic table, 8A, they don't have a pattern. Okay? All right, so there's one last vocabulary word here that goes with that sort of general rule we just talked about, and that is oxidation number. Okay, so an oxidation number is this charge, this positive or negative of an atom based on the number of electrons it's going to gain or lose. Okay, and we can actually look at the periodic table and we can predict the oxidation number, the expected charge, or the expected number of electrons that an atom is going to gain or lose. Okay? It turns out, and it would help if you got out your periodic table and looked at it, okay, lithium is in group 1A. All of the elements in group 1A are going to take a +1 charge, meaning they give away an electron. And magnesium and all the other elements in group 2A are going to give away 2 electrons. They've got 2 electrons in their outermost shell. They give them away. They take a +2 charge. Group 3A, skipping the transition metals, which are unpredictable, unfortunately. Group 3A, they've got 3 electrons in their outermost shell. They're going to get rid of them, form a +3 charge. Okay, carbon, some of the other elements in its column, they've got 4 electrons, so they're going to try to steal 4 more. Okay. Group 5A, they've got 5 electrons, so they're going to try to steal 3 more. Group 6A, they've got 6 electrons, they're going to try to steal 2 more. In group 7A, they got 7 electrons, they're so close, they're going to try to steal 1 more. So, we will get this all written onto our periodic table and work with these ideas the next time you are in class.